All right, we're diving deep into the incredible world of 7 nanometer transistors. I mean, these things are so small you could fit thousands of them on the tip of a single human hair. We're going to explore how engineers can build a perfect digital copy, a digital twin, to predict exactly how these tiny switches will behave before a single one is ever made.
But that brings up the big question, really the central mystery of this whole explainer. See, at this tiny scale, a transistor isn't an island anymore. Its performance, even its basic identity, gets shaped by its surroundings, its neighborhood. So why does this local environment all of a sudden have such a huge and often problematic influence?
Well, the answer is all about invisible forces. In these advanced FinFET transistors, the whole environment is just incredibly dense. If you look here, features like this gate cut, which is basically an endpoint for the transistor's gate, create these immense mechanical stresses. These forces, what we call local layout effects, or LLEs, can literally squeeze and stretch the transistor, and that changes its electrical behavior in really unpredictable ways. Honestly, this is one of the biggest headaches in modern chip design. So, how in the world do you tackle something like that? Well, here's our roadmap. We'll start with the challenge itself. Then we'll get into the blueprint, which is this really cool dual-branch workflow. We'll look at the physical silicon side, then the digital TCAD side, see how they come together, and finally, check out the big payoff for chip designers. Okay, so the heart of the solution is this dual-branch workflow. The main idea is that to get this right, you have to operate in two worlds at the same time, a physical world of real-world measurements and a virtual world of digital simulation. You can't just pick one. They have to run in parallel, working together. Here's how that whole process looks. Everything kicks off with the device layout. From that single point, the process literally splits. You've got the silicon branch, which involves actually making and testing real chips. In parallel, you have the TCAD branch, where you're using powerful software to build a virtual model. Then comes the magic, the convergence point, model calibration. This is where the digital twin gets tuned and refined against all that real-world data to finally spit out an accurate performance prediction. Let's dig into that silicon branch first. Its whole job, its entire reason for being, is to create a rock-solid foundation in reality. We're talking about creating the ground truth that our digital model will have to answer to. And they do this at a pretty incredible scale. I mean, to even start seeing these super subtle layout effects, engineers can't just test a handful of devices. No way. They have to manufacture and measure over 30,000 transistors on one dedicated test chip. It's only with that massive amount of data that those tiny systematic changes start to pop out from all the background noise.
But here's the thing. It's not just about the raw numbers. The real key, as the source material puts it, is statistical discipline. Each one of those 30,000 plus devices is part of a super carefully designed experiment built to isolate one variable at a time. It's this rigorous approach that makes sure the data is clean, reliable, and a perfect anchor for our digital twin.
Now let's jump over to that other parallel path, the TCAD branch. This is where we step out of the physical lab and into the world of simulation to start building our virtual copy. And this is so much more than just a 3D drawing. The TCAD model is a really sophisticated physics-based simulation. It digitally recreates the entire manufacturing process, everything from etching the fins to depositing the gate materials. It builds a virtual transistor that captures its exact geometry, its materials, and most importantly, those critical stresses that get baked in during manufacturing. And that brings us to the most crucial step of all, the convergence. This is where the silicon data from the physical branch and the virtual model from the digital branch are finally brought together. It's the moment the digital twin gets to learn from reality and becomes truly predictive. Now, the calibration itself happens in two very distinct phases. First up is process calibration. Here you're just trying to make sure the model's physical structure, like the thickness of its layers, matches up with the real thing. Only after that structure is locked in do you move to phase two, electrical calibration. Now you tune the model's physics to match the measured current and voltage. This two-step process is absolutely vital. It prevents what's known as curve fitting, which is basically just faking it. This ensures our model isn't just mimicking the data, it's genuinely representing the correct underlying physics. And the core piece of physics it uncovers is this. Mechanical stress isn't just one single number. You can't just say a transistor has X amount of stress. It's actually a 3D tensor, which is a fancy way of saying it has both a magnitude and, crucially, a direction. So this 3D tensor can be broken down into three main components. You've got longitudinal stress, which runs along the direction the current flows. Then there's vertical stress, pressing down from the top. And finally, transversal stress, which squeezes the fin from the sides. Each one of these has a completely unique effect on how the transistor performs. And this is why understanding that 3D stress is so critical. It explains the night and day difference between PMOS and NMOS transistors. For PMOS devices, performance is almost all about that longitudinal stress. In fact, for them, compressive stress actually improves their performance, which makes their behavior strong and predictable. But for NMOS, it's the total opposite. That same compressive longitudinal stress degrades their performance. And on top of that, they're affected by a messy mix of all three stress components. That makes their behavior a lot weaker and way harder to predict. So we've gone through all this work to get this incredibly accurate, physics-based digital twin. But what's the ultimate payoff? Well, it's all about building a bridge from all this deep physics to the practical tools that circuit designers use every single day. And this table right here, this is that bridge being built. You can see how the insights from the TC-CAT simulation, like how a gate cut changes the stress, get translated directly into these industry-standard model parameters. Those parameters then get fed into SPICE simulators, which are the software tools chip designers live in. So all that complex physics of stress gets baked right into the models they use to design chips with literally billions of transistors. You see, by building this physically anchored digital twin, the industry can completely shift its approach. We can finally move away from just observing problems after they happen and move towards predicting and preventing them before a design is even finalized. And that kind of leaves us with one last big thought. We now have the power to create a near-perfect digital copy of one of the most complex things humans have ever made. So if we can do that for just a single transistor, what does that mean for the future of designing entire systems? What's the next big frontier for the digital twin?